Hi, welcome to the last of the three tutorials on probability and statistics. Now we'll talk about joint distributions, marginals, independence, as well as conditional distributions and conditional independence, and of course Bayes' theorem. I'm assuming all of you have already seen the multivariate integration and differentiation and stuff like that was introduced in the earlier tutorials. Now for the discrete case, for the multivariate distribution, it is simply specified by the, just like we were specifying p of x equal to x for the case of a one-dimensional PMF. Here we just have to specify pxy of x equal to small x and y equal to small y for all x and y in the domains of capital X, capital Y. Right? The entire set of such values must sum to 1. And for example, if I was tossing, if x was the result of one coin toss and y was the result of another coin toss, then we can say that the probability that, for example, x is heads and y is tails is 1 by 4. And you can specify each of these. The probability that x is tails and y is tails is also 1 by 4, and so on. So you can, as long as you specify these for all x and y in your domain, and as long as they sum to 1, that's a valid discrete distribution. You can also specify it by specifying the CDF. Remember, the CDF always works, and so instead of specifying these explicit values, you can also specify this function, which is fxy, capital Fxy of x comma y, which is exactly the multivariate version of the CDF. It's the probability of x less than equal to little x and y less than equal to little y. Now for the continuous case, instead of specifying pxy, we would specify the PDF, which is fxy of x equal to x, y equal to y. And this must integrate to 1. Remember, this is not the probability of observing little x and little y. That probability would be 0 for a continuous distribution. But it gives, the only way to interpret this would be to say that when I integrate over some domain fxy, then I basically get the probability that x comma y will lie in that domain. When I draw a random sample x comma y, what is the probability that it lies in that domain? It's given exactly by the integral of over that domain of fxy. So the only interpretation, just as before, of a PDF is through integration and not just by itself. The ratio of two of these PDFs can give the relative likelihood of observing two values, but it does not give the probability of observing a particular value. Again, a PDF can also be specified by a CDF. So if you want to describe a multivariate continuous distribution, you can either describe its PDF or you can describe its CDF. So what is a marginal? The marginal of x is given by px x equal to t, which is the summation over all y of probability of x equal to t and y equal to little y. So basically you take a joint distribution and you sum over all the possible values that the other variables can take. Of course, if there were several other variables, this would be a multiple summation over all those other variables to get the marginal for one variable. Again, to get a marginal for two variables out of 5 variables, then you sum over the other 3 variables, over all the possible values over the other 3 variables. In the continuous case, the summation is actually an integral, and that's represented by the PDF of x at the point t is given by the joint PDF at t and y. So this is the joint PDF of x, y, right? And integrated over all y. Again, if I wanted the marginal of 3 variables out of a total of 5 variables, then I integrate out the other 2 variables. So a marginal distribution is just like one slice of a joint distribution in some sense. It You integrate out the effect of the other variables to only characterize the effect on a subset of the variables. Now x and y are independent if and only if the joint distribution is the product of the marginals. So this is what it is. This is how you would characterize it for discrete distributions. For continuous distributions, we say that the PDF, the joint PDF of x and y, is the product of the marginal PDFs. And this must hold at all points x and y in the domain of capital X and capital Y. Great. So that's what independence is. Basically says that the joint is the product of the marginals. Now the expected value of z when it's a vector, when you have a vector x comma y, the expected value of z is basically the expected value of x comma the expected value of y. So it's just a vector where you take the expected value of each component of the vector individually. And what happens is when you take the expected value of x, you basically get integral of x f of x comma y. So this is say little x, f of x comma y dx dy. And now we can integrate with respect, we have to integrate with respect to x and y. So let's say this is over the x domain, this is over the y domain. Then we can first do the integral over y. So if you remember what we talked about in the tutorials on multivariate calculus, you can first do the integral over y. This is the integral over y of f of xy dy. That's precisely the marginal of x. So this expected value of x just ends up being integral x f of x dx. And this is what we knew was the original definition of expected value of x when it was just a univariate quantity, when there was no vectors involved. It turns out that if you have like a bivariate or a multivariate distribution whose expected value you're calculating, you can actually take the marginals and calculate the expected value of the marginals individually, and that gives the expected value of the distribution. Now, the expected value of some other function g of x comma y is just in the multivariate case given by, very much similar to the univariate case, it's the integral over x and y, g of xy f of xy dx dy. So of course if g of xy is just x, then that's what we get here. If g of xy is just y, then that's what we get here. But in general, g of xy could be some other function of x and y, in which case the expected value of g of xy is given by this quantity. Lastly, the variance is now a matrix. Earlier the variance was just a scalar, but in the multidimensional case, it's actually a covariance matrix. And it is the expected value of z minus expected value of z times z minus expected value of z transpose. Now that might seem a little confusing, but let's break it up into two parts. First, find the mean of z, which is a mean vector. Okay, so that's what we plug in over here, and so we calculate. Let's call that mu for the moment, right? So that's just mu. So we calculate z minus mu times z minus mu transpose. So remember from our earlier linear algebra tutorials, we have v transpose. This is basically a matrix. It's a single quantity like this is a rank 1 matrix. Now we're taking an average of many such rank 1 matrices. It's usually a higher rank or sometimes even a full rank matrix, and that's exactly what the covariance matrix is. It is the expected value of this VV transpose, where V is this Z minus mu. And what is the expectation over? It's the expectation over Z drawn according to the joint distribution of x and y. Right? So maybe Pxy. So let's just recap. We define the marginal of x, which is integrating out some of the variables. We define independence in terms of the marginals of x. We define what it means for the expected value of a vector and the expected value of multivariate functions. And we define the covariance matrix. The interpretation of the covariance matrix is basically, suppose Z is an n-dimensional vector, real vector, then the covariance matrix is an n cross n matrix. Remember, because this is n cross 1, this is 1 cross n. So when you take this product, this outer product, you get an n cross n matrix, and when you take the expectation of n cross n matrices, it's an n cross n matrix. And the interpretation of this n cross n matrix is basically something like, how does the ith component of z, the ith random variable in the random vector z, how does that vary with the jth random variable in the random vector z? And that's what will be given by the covariance matrix ijth entry. It's like, how much does the ith vector vary with the jth vector? If the ith and the jth vectors were independent, then you would actually have a value of 0 there. If they were not independent, you wouldn't have a value of 0 there. And so that's what the entire matrix is. It's like, for all I and j, how do they covary? That's why it's called a covariance matrix. The last part that we'll talk about is conditional distributions and Bayes' theorem. Now, the conditional distribution is defined in the following way. P of xy is defined to be P of x comma y by P of y. And now if you actually expand that out, sometimes it's just written like this, but what that really means is that the probability that x takes the value s given that y takes the value t is actually equal to the probability that x takes the value s and y takes the value t divided by the probability that y takes the value t. Now when you have a multivariate distribution, this is basically from the joint distribution of x and y, right? So this is what we actually have. We have pxy, we have some way of specifying this multivariate distribution pxy, and the denominator is the marginal py, right? So the conditional is the joint divided by the marginal. And some example of when you might want to do this is, for example, when you calculate what is the probability that the first die had a 6 on it, if I give you the fact that the sum of the first two die had a total of 7. For example, instead of 7, if I had the value 12, then the probability that the first die was 6, given that the sum of the die is 12, is exactly 1. Right? But if I just look at the marginal probability, which is just what is the probability of the die being 6, it's 1 by 6. But given that the sum of the first two dice is 12, that probability ends up being 1. Now we get to Bayes' theorem. This is one of the most important theorems that you'll see throughout machine learning, so it's probably good to get a hold of what it's saying. It's just a restatement of the definition of conditional probability. Now, by the definition of conditional probability, we have the fact that P of A comma B, which is the joint, can be written as P of B given A into probability of A. That just happens by taking the denominator to the other side, right? So then we get P of B given A by probability of A is the left hand side, and the right hand side is the joint. Now another way of writing that is P of A given B into probability of B. That's also P of A comma B, right? So given these two different ways of decomposing P of A comma B, we can actually equate them, and we get basically what Bayes' theorem says, which is the probability that A is equal to S given that B is equal to T, right? That's the left hand side, is the probability that B is equal to T given A is equal to S times the probability that A is equal to S divided by the probability that B is equal to T. So I've just rearranged this by taking this term to the other side. Now if you remember the definition of the marginal, we can further expand it. The definition of the marginal is that P of B is equal to T is exactly the summation of the joint distribution of P of B equal to T and A is equal to S over all S. That's the definition of the joint. But remember that this, by conditional properties, can be expanded as this. That's just literally by the definition, that you can expand the joint as the conditional times the smaller marginal. So sometimes you'll see this term appearing in the denominator of Bayes' theorem. That is the entire expanded out statement. But basically, Bayes' theorem is a way of getting the property of A is equal to S given B is equal to T from the reverse probability, that is the property that B is equal to T given A is equal to S, and the property that and the marginals of A is equal to S and B equal to T. For continuous variables, it's quite important to remember that we don't deal with such probabilities, but we deal with distributions. So these are PDFs that we'll deal with, and it says that the PDF of X given Y takes the value Y, little y, is the PDF of Y evaluated at Y given that X takes the value little x times the PDF of the marginal PDF of X at X divided by the marginal PDF of Y at Y. So it's exactly the same as what's over here, right, where A is X and B is Y. That's the only difference, except that instead of using probabilities, we use distributions, PDFs. We use PDFs. And remember that one can find easy intuitive examples where this perfectly makes sense. It might be a little harder to wrap your head around this statement, because this statement is not about probabilities, but it's about PDFs. And remember, the only interpretation of PDFs is through integrating the PDF and talking about how much probability mass lies in that domain over which you integrated. It also has an interpretation through relative likelihoods by dividing PDFs, but you'll probably see that at a later point. Lastly, conditional independence holds if P of X comma Y given Z is P of X given Z into P of Y given Z. Now remember that marginal independence, or just plain independence, was when Z didn't exist. There was no Z term. It was just P of X comma Y is P of X times P of Y. Now conditional independence has a given Z on all of those terms. Hopefully you will see more examples of these online on Wikipedia and so on, or maybe in your recitations or in classes, but that's all I have to say for the moment. In summary, this is what we completed: events, probabilities and random variables in the first tutorial, distributions, mean, median, variance, mode and so on in the second tutorial, and the last tutorial covering joint distributions, marginals, conditionals, independence and Bayes' theorem.